and grading done. Woo! Nice.
Hey, Miss Lanigan.
Oh, hey, what's up?
Have you seen Mr. Corbett?
Yeah, a few minutes ago he was running down the hall with a pickaxe and a shovel, wearing goggles, and he had a pool noodle.
Oh, like a pool?
Like one of your pool noodles that you keep in your classroom.
Huh. Well, we've got a train to catch soon.
Where are we going?
The Pacific Northwest Seismic Network.
Oh, I forgot about that. Okay, let's go. Mr. Corbett.
Where are you?
Miss Lanigan, Mr. Hansen, I've got a perfect plan. You know the Wanda plate? Wait, the Wanda.
What's he holding?
The Wanda Fuca plate? The Wanda Fuca plate off in the Pacific Ocean. I heard a story that it might be a huge earthquake. The whole thing might pop up and it might have a giant tsunami. So I've decided to be a hero. Salty. So I'm going to take this pickaxe, now that I've lubricated it with some snot. I'm going to dig down in the Pacific Ocean. I'm going to get down into that fault line, and I'm going to put some grease in it. That way it just slides real easy. I don't want none of this popping up rough stuff. Today, boogers save lives. I will stop it from happening. To the fault!
You can't lubricate a tectonic plate with boogers. Say something.
Hello?
Quietly.
Can you hear me now? Can you hear me?
What are you doing?
Oh, hey, Miss Lanigan. I got this subduction model here. I know that one of the plates is diving under the other plate, but I can't seem to figure it out. I feel like I need to phone a friend, someone that really knows a lot about this stuff.
I think we might know somebody.
Perfect.
I think he might be right there. Mr. Hansen was trying to figure out what's going on here with the Cascadia subduction zone, so maybe we can get a better idea from the expert here.
So the subduction zone, where the oceanic plate, which is the Wanda Fuca plate, is subducting, basically diving underneath as part of this convective cycle, underneath the Pacific plate, or pardon me, the North American plate, we are compressing the leading edge of the crust as this zone is actually locked. It's not a smooth conveyor belt. We're actually having what we call a stick-slip process go on out here. And over the course of hundreds of years, we build up energy along the leading edge of the continental margin. The continental margin actually compresses, which we can see with GPS. And then after 300 to 500 years, there's too much force built up along the subduction zone, and we slip. We actually move laterally east to west, dozens of feet. We compensate for the motion that's been stuck for hundreds of years.
When was the last time this happened?
The last time we had a large subduction zone earthquake was in the year 1700. And if we do the math, it's been 325 years. Now that doesn't mean we're overdue for an earthquake. That means we're at the leading edge for that expected window. Now that window is 200 years wide. We can have an earthquake in the next few years or 200 years down the road, and both of those times would fit within the average window. We can see back about 16,000 years in geological time using offshore mud records, and we see a large subduction zone earthquake every 300 to 500 years on average.
In scientific terms, when we say any day now, nothing's certain, right? So if our colleague were to go in and lubricate this area so that it just went smoothly, do you think that's something that could actually be done?
I don't think it's feasible, but because of how young the Wanda Fuca plate is, there is actually more water within this plate than there is in other parts of the Pacific plate, which some people think may contribute to our lack of earthquakes. There may be actually lubricant in there already.
Ooh.
But in the grand scheme of things, it is locked. And I don't know if there's a way to stop plate tectonics. Ultimately, over thousands of years, tens of thousands of years, this subduction zone is going to continue to build up and release pressure on a pretty routine interval.
How far down can they tell where it's stuck?
The subduction zone is locked from the leading edge out on the ocean to somewhere kind of deep underneath the leading edge of the Olympic Peninsula. That's what we call the locked zone, where the two plates are actually stuck together.
Right.
Further on down the subduction zone, the plate actually begins to really dip and fall off, where the plates actually become uncoupled. And you can see that on the image right there. Those orange dots, like the Nisqually earthquake, the most common earthquake we have in Washington and Oregon, those aren't due to the friction, the locked nature of the subduction zone. That's actually where the plate is beginning to fall apart and melt.
Oh.
Those earthquakes have their own reoccurrence interval of about once every 30 to 50 years in Washington and Oregon.
Okay. That one could happen. Anything.
That one is more likely,
Yeah.
certainly. The last one was in 2001. It's been 24 years since we had a large, deep earthquake like that. And so I would expect one sometime in the next several years in Washington and Oregon.
And can you predict the magnitude of that?
Those large earthquakes are on the order of magnitude 5 to 7.
So we feel it.
We would certainly feel that. That could potentially damage our homes and
Okay,
communities.
that's nice.
The Nisqually was a magnitude 6.8, but was actually so deep, by the time that shaking spread to the surface, it was felt over a really wide area. But right over the epicenter was not as strongly felt. Unlike a California earthquake, which is really shallow, focuses all that energy over a small area.
So the Cascadia subduction zone where it's stuck, do you know how, like in kilometers or meters or miles or feet it is where it's stuck?
From right along the surface to about 10 to 12 kilometers, I believe. Our Nisqually style earthquakes are about 40 kilometers beneath our
Okay.
feet. Earthquakes within the crust are within the top handful of kilometers. And then deep beneath our feet, unlike in California, we have earthquakes on the subducting slab beneath us that are about 30 to 40 kilometers below our feet. There are old fault lines throughout all of the Intermountain West and even into the eastern portions of the United States. It's much less active, of course, but there can be large earthquakes, but they're much more infrequent.
So those are more like faults, and these are more like, these are plate boundaries. that
These
we're
are plate
talking about.
boundaries, exactly.
So
right.
there's faults all over the plate,
Yep.
but there's actual plate boundaries where they're
Yeah.
separating or coming together or sliding side by side.
Right, there are crustal faults all over the continent, and the most active ones are on the margins. The most active margin is the west coast because we have a subduction zone and active tectonics here. But the crustal faults throughout the continent are active for other reasons. The subduction zone boundary is where most of the energy and most of the plate motion is going on. You're right.
Got it. Good.
So every time we go up a whole number on the magnitude scale, we increase the energy by a factor of 32. So here's a damaging earthquake in Napa, California. Here was the earthquake that cracked the Washington Monument, magnitude 5.8 on the East Coast. And as we zoom out, every time we go up a whole number, we increase the size by 32. There's 32 magnitude 6s inside our magnitude 7. Our Nisqually earthquake is right here, magnitude 6.8. The Loma Prieta earthquake in California, which was very damaging over a small area, is right here. And as we zoom out, the difference between our magnitude 7 and our magnitude 8 is again a factor of 32. There's 32 magnitude 7s inside of a magnitude 8. And so this exponential scale shows why we have different types of seismometers. There's very, very small shaking and there's great shaking that we record. And now even our magnitude 6.0 is becoming the size of a pixel as we compare it to the largest earthquakes on the planet Earth. There is an upper limit to this scale. When scientists created the scale, they set 10 as sort of the outer limit of the magnitude scale. And so we get up to these great earthquakes, the largest earthquakes ever recorded, magnitude 9s, Even our magnitude 7 is going to begin to disappear. Our magnitude 6 is completely less than a pixel size and is gone off of here. So we've got the largest earthquake in United States history, magnitude 9.1, pardon me, 9.2 in Alaska, the most deadly earthquake in world history because of the tsunami, the Sumatra earthquake 9.1, and almost 3 times bigger than those, the largest earthquake ever recorded, magnitude 9.5 in Chile.
Why would there not be an earthquake of a 10 magnitude?
Good question. That's because to get a big earthquake, you need a big fault line. The fault lines on the planet Earth just aren't big enough to create a magnitude 10, which would be about 3 times bigger or more than the 9.5. Our fault lines just aren't long enough. On a bigger planet somewhere in the universe with bigger fault lines, you could get a magnitude 10, but not here on Earth.
Mr. Corbett,
Where are you?
what are you doing now?
What's
Mr. Hanson, Miss Lanigan.
he holding?
What? It's a pool noodle. He must have got that from you.
Oh, it's a crazy sea out here. I told you I'm gonna save that Wanda. Wait, no, Wanda hookah plate. It's going down. I'm ready. I just gotta get there. It's just so hard. Who thought about bringing this pool noodle? Idiots! What am I gonna do now? I got no more. Fingy paddles.
Mr. Corbett,
Is he underwater?
where are you?
The,
What is going... Did you hear something?
no, I thought I saw something, no?
Me too. But
Clearly it's underwater.
he... Mr. Corbett!
Dang it. Ooh. Ocean food.
Mr. Corbett!
Hello?